Now, let's take a look at how we can implement our naive string class, which really highlights the core concepts of dynamic memory management in C++. This class starts off with a private member, p, defined as a pointer to char, which will hold our dynamically allocated string. So, in the constructor, we take a C-style string as input and allocate sufficient memory on the heap to store that string. Don't forget, we also add an extra byte for the null terminator. By using new, we ensure that the memory is allocated dynamically, really aligning with our focus on resource management. Next, we copy the input string into that allocated memory using the strcopy function. This is crucial because it ensures that our naive string has its own copy of the string data instead of just referencing the original C-style string. Now, it's important to talk about cleanup as well. We must define a destructor for our class that will handle releasing the allocated memory when the object goes out of scope. So, by invoking delete dash on p, we effectively prevent memory leaks, which is absolutely a critical aspect of memory management in C++. This careful construction demonstrates the real importance of having proper cleanup logic to maintain efficient resource handling within our application. The displayed figure titled Key Concepts in Resource Management presents a bar chart where the x-axis lists 5 distinct concepts: destructor importance, memory leaks, dynamic allocation, object lifetime, and resource management. Meanwhile, the y-axis quantifies each concept's importance level %. Each bar is annotated with its exact numeric value above it. Destructor importance at 80%, memory leaks at 60%, dynamic allocation at 75%, object lifetime at 90%, and resource management at 85%. So, what can we conclude from these values? Well, first and foremost, we see that object lifetime is rated highest at 90%. This indicates that controlling when objects are created and destroyed is viewed as the most critical aspect of resource management. Right behind it, we find resource management at 85%, which emphasizes the broad responsibility of classes to handle resources correctly. Now, destructor importance, sitting at 80%, underscores the need for explicit cleanup logic. This is something we really saw in our naive string destructor example. And then we have dynamic allocation at 75%, highlighting that allocating memory on the heap is a substantial part of the problem space we're dealing with. Even though memory leaks come in at 60%, which is numerically lower than the others, it still represents a significant concern, suggesting that while leaks are indeed something we need to prevent, our chart emphasizes proactive design elements like object lifetime and resource management more strongly than it does the leaks themselves. Taken all together, these plotted values reinforce a very important lesson. We must prioritize clear ownership and lifetime semantics, and ensure that destructors, or even automatic mechanisms, handle cleanup to avoid the practical consequences represented by those memory leaks. Now, let's take a look at how we can implement a simple, naive string class that manages dynamic memory. This class features a private member, p, which is essentially a pointer to a dynamically allocated array that holds our string. So, when we create an instance of naive string, using the constructor that takes a C-style string as input, we allocate memory with the new operator based on the length of the input string. Next, we recognize the significance of proper memory management by incorporating a destructor. Although it might seem like we can skip it, a destructor is crucial for cleaning up the allocated memory when the object is destroyed. This cleanup is done through the delete shell operator, which we must invoke on p to avoid memory leaks when our class instances go out of scope. Through this approach, we're highlighting a fundamental principle in C++ resource management. It's vital to ensure that whenever we allocate resources, we also define a clear strategy for their deallocation. As we proceed, we'll further elaborate on how encapsulating this functionality correctly guards against memory mismanagement, showcasing the essential role destructors play in maintaining system performance and stability. All right, let's dive deeper into this concept as we explore practical examples. Now, let's see how we can expand our naive string class with a copy constructor and an assignment operator to enhance our resource management. In this implementation, the copy constructor ensures that when we create a new instance of naive string from an existing one, it allocates its own separate memory for the string. This is crucial to prevent multiple objects from sharing the same memory address, which could lead to issues if one object deallocates the memory first. Now, moving on to the assignment operator, before we assign a new value to an existing instance, it first checks for self-assignment to avoid unnecessary operations and potential errors. If the object isn't self-assigning, it will delete the existing memory allocation to prevent memory leaks, then allocate new memory for the incoming string from the other instance. This method helps ensure that the class maintains proper memory management throughout its lifecycle. And finally, we include a destructor that deallocates the memory pointed to by P when the object is destroyed. This three-part approach, combining the copy constructor, assignment operator, and destructor, forms the well-known rule of three in C++, which is essential for maintaining resource integrity in any class that manages dynamic memory. Now, let's dive into how we can implement a function to display the contents of our naive string class. The displayString function is carefully designed to take a constant reference to a naive string object as its parameter, which ensures that it doesn't modify the original string while providing efficient access to it. Inside this function, we utilize the get method, the one we assume is defined in our naive string class, to retrieve the character pointer that holds our string data. When we call this function, it outputs the string to the standard output using stdcout, followed by a new line. This approach not only encapsulates the behavior of displaying the string, but also reflects how well our class manages resources, keeping functionality clean and user-friendly. By using a constant reference, we ensure that the contents of the string are displayed without unnecessary copying, which really enhances efficiency. As we continue with our implementations and put the functionality of naive string to the test, this display function will become essential in validating that our resource management strategies are working as intended. It reinforces all those principles we've learned about effective memory handling, and, trust me, it's really key to our progress. Now, let's implement the naive string class using smart pointers to enhance memory management. In this version, we utilize stb_unique_pointer, which automatically handles memory cleanup when the naive string object goes out of scope. The class features a private member, P, that stores the unique pointer to a dynamically allocated character array. In the constructor, we allocate memory for the string using new char stringlen str+1, ensuring that we're copying the content of the provided C-style string into this allocated memory. By using p.get, we retrieve the raw pointer to pass to strcopy, which lets us fill the allocated array with the string data. Now, here's the real beauty of this design. It eliminates the need for a manual destructor, since std_unique_pointer automatically frees the memory used by P when naive string is destroyed. This significantly reduces the risk of memory leaks. Additionally, we've included a display method that neatly prints the string stored in our unique pointer. By implementing resource management with smart pointers, we simplify our code and ensure a safer memory handling strategy, while allowing us to focus on higher-level functionality.